second way that we can constrain the system is by doing reactions at constant pressure. So I said that this one was a little bit more complicated. Now, it's more complicated only in terms of how directly we get information from the reaction, but in terms of doing chemistry, this is how you've done every chemistry experiment in lab up until this point. So when we do reactions just kind of open to the atmosphere or out on the benchtop, this is a constant pressure situation. So constant volume, which we did in the last video, makes our math directly really easy, but in terms of the setup, we need some complicated things to make sure that the volume of our reaction doesn't change. So when we do things at constant pressure, one complication that we are going to address, how we get rid of it, is that at constant pressure, our delta E reaction, so change in internal energy for the reaction, still has contributions from heat and work. So keeping the pressure constant doesn't eliminate any of these terms. However, we don't often care about the work. First of all, sorry, work. And the contribution from work is sometimes really small. And I'm going to kind of try to draw you a picture to show why. So it's sometimes so small that it doesn't change our calculation value anyway. So if you could imagine that you had some reaction, and we're just going to put a little Erlenmeyer, and we have some reaction going on in here, and the reaction is the system, and then we have our surroundings. If we want to know about change in volume, how might you measure that? So if it's something that's a gas, we could put it in a piston and have that go. We could measure it that way, but a lot of the reactions that we do are solution reactions. So, and even if it gave a gas as a product, this experiment, this flask that we have, it's open inside your fume hood. So, okay, well, that's some volume, but your fume hood is open to the classroom, and the classroom is open to the whole building. I mean, even if we have the door shut, right, there are cracks around it, that volume isn't a fixed value in terms of where gases can go. Well, the building is open to the outside. So the delta V, because the original volume of almost the universe basically is so huge, the delta V is so tiny that this term doesn't contribute to what we're looking at for our delta E reaction very much anyway. And that also makes it really hard to measure, so we kind of don't care about it. So the heat ends up being the part that's a lot bigger and the part that we care about a lot more. So what chemists have done is they have said, we want to talk about the heat at constant pressure. What we're going to do is talk about something called enthalpy. We're going to give it this special term, and we are going to define enthalpy, and we use the letter H for enthalpy as the internal energy plus the pressure times the volume. Okay, this is kind of weird, but let's keep going. Enthalpy is a state function. Well, that's kind of nice. So if it's a state function, that means we can just do final minus initial to figure out changes. Our delta H is going to be delta E plus P delta V, right? No delta P because we're doing constant pressure. Well, delta E is Q plus W. Well, if W is negative P delta V, a positive P delta V is just negative work. So enthalpy is what happens when you subtract the work from the internal energy. So all of the work goes away and we're left with just the heat at constant pressure. So enthalpy, delta H, is heat, but this time we give it a sub P because we mean heat at constant pressure. And so now we can just go through, do our reactions as long as we're running them at constant pressure, and we measure the heat. We can say that that is the change in enthalpy for that reaction. It's really, it's a useful value, and we're going to talk about what you can use it for, but it's also really convenient because doing chemistry just open to the air is how we're used to doing things, right? It's the easiest way for us to run reactions. So you have seen some information about reactions before. It's kind of had a delta H with it because of the order that we've covered these chapters in. So we're just going to do a quick summary here to remind you. So an endothermic reaction is a reaction that absorbs heat from the surroundings. It has a positive delta H value. So just like the heat value was positive when something was absorbing heat, well, because that translates directly to enthalpy, if delta H is positive, then it's an endothermic reaction. I'll say and absorbs heat. And it's always going to get that heat from the surroundings. An exothermic reaction has a negative delta H. Right, so Q is negative when heat is given off. So delta H is negative when heat is given off. So it gives off heat. And that heat is then absorbed by the surroundings. So we do need to say a little bit about stoichiometry and how it fits with delta H. It will be exactly like what we saw in our bomb calorimetry example. This delta H reaction, or enthalpy of reaction, or heat of reaction is what it'll sometimes be called since it's coming directly from that heat value, is an extensive property, which is just the fancy word for what we saw in the previous problem, which means it depends on the amount reacted. So typically you'll see this paired with a balanced reaction. And so when it's with a balanced reaction, it is for stoichiometric amounts. So the reaction I'm going to give you as an example is C3H8 gas combusting. So if I combust 1 mole of C3H8 gas, which means it's going to react perfectly with 5 moles of oxygen, and we're going to get exactly 3 moles of CO2 and 4 moles of H2O as product. The delta H reaction written next to it would be negative 2044 kilojoules. What this means is that when 1 mole of C3H8 is reacted perfectly, you get exactly 2,044 kilojoules of heat given off, which is why it's negative. So this tells you a couple of things. One, you could write this as negative 2,044 kilojoules per 1 mole of C3H8. Well, this, in this form, looks awfully lot like a conversion factor, and you can use it that way. So if you wanted to know, for example, how much heat is given off when 0.248 moles of C3H8 is burned, you could calculate this, right? So we have 0.248 moles C3H8, and I know that I get negative 2,044 kilojoules for every 1 mole. So I would get negative 506.9 kilojoules of heat off from burning that much C3H8. So this will set you up to do a number of things. So it could be that you know how much heat you need. Say you're trying to heat up some water. You could figure out how much fuel do I need to combust in order to get the amount of heat that I need. And because this goes with the balanced reaction, you could put any other piece in here, right? So if I am only capable of measuring how much oxygen I use up, well, I know that I give off negative 2,044 kilojoules of heat for every 5 moles of oxygen I use up. And you could do it for 3 moles of CO2 produced or 4 moles of H2O produced.